Good afternoon, Fancy Meat Computers. How's everybody doing this fine, lovely, somewhat gray afternoon in the middle of November? My goodness, we're closer now to December than we are to October. This is a month that is progressing quickly, or perhaps not. Depends on your subjective standpoint. How is everybody? How's everybody doing? Do we have anybody in the audience? Are you still there? One person is watching. Four people are watching. 7 people are watching. Okay, so we do have some people. That's good. 10, and that's the magic number. It's never there to begin with. Wah, wah. Ba, 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 ba. Wah. Okay. Yeah, I think we'll give it a minute or two to wait for the rest of everybody to show up. So I expect I'll probably be able to get Project 3 together and out for your project writing pleasure sometime today. It's going pretty well. I actually kind of I started working on it a few weeks ago, and I kind of crumpled up the paper virtually, threw it over my shoulder, and started over again on what I want for the project, because it was originally it was just do a type system for UAE and TLC, but as the course has progressed, this project feels more and more like a summative assessment. So I really wanted to work in some of the stuff we've been covering in more recent weeks, like the sequencing operator and references. So essentially, as a summative project, the idea is that you're going to take a selection of the language constructs that we have done so far and implement them in Haskell in the same way that you've been implementing the smaller languages that we've been doing so far. So it's like all of UAE, or all of untyped arithmetic expressions, all of lambda calculus, like simple lambda calculus, combined with unit sequencing, let bindings, and all of the reference operations. And it's like build a semantic, like build the small step operational semantics for it in the same way that you should be used to by now, and then also build a type checker. Do an eval operation, which is the multi-step operational semantic, or the multi-step small step operational semantics. Just, goes through multiple iterations of the small step semantic until you hit a value or a normal form, and then a run function. And the idea is that the thing invokes the type checker before it tries to execute, and if it doesn't type check, it doesn't execute. Basically. So yeah, it's kind of interesting actually, because like, as I'm sort of fleshing this out in this project, it turns out that the sigma thing is a little bit tricky. Like, I'm actually not a huge fan of the manner in which the textbook approached things with the sigma, now that I'm actually trying to implement it. So I'm probably going to make some modifications to the semantic that you guys are to implement that kind of dispenses with sigma entirely. It'll be like, it'll kind of be like, basically my plan is for, like, if we can restrict it so that allocation is only applicable inside of a let binding. It sounds like this would be easier to do in Go. Well, no, it's not because of the statefulness problem. It's a problem of the separation of the type checker from the evaluation semantics, right? Like, it doesn't matter what language you'd be implementing this in, you'd still be running into a problem if you, like, you would run into the same problem in Go, which is that you really should not make the type checker dependent on evaluation semantics, right? That's not cool. So the method that's proposed the method that's proposed in the textbook of, like, maintaining a separate sigma store for typing is like, So the idea that I'm sort of developing at the moment, that I'm going to develop to the point of execution today, once I deal with a certain plumbing problem that has occurred in the kitchen sink. If we restrict allocation to only occur during a let binding, the semantics for let bindings are very similar to the semantics for lambda abstractions, in that they add to gamma, right? So if we make it so that the allocation step can only occur inside of a let binding, then we can basically piggyback on gamma to type locations, which, I'm still working out the details. And of course, I'll make this all very, very explicit in the document. But yeah, so that's currently the issue I'm working through with respect to the project. But, if that's the only issue that we're having, then we're doing pretty well. Because, like, in theory, yeah, well, at any rate. like, if the location is bound to the variable, and the variable has a typing in gamma, then you can type that from the variable in gamma without having to evaluate it to a location and then finding that location's corresponding entry in sigma, because that requires an evaluation step, minimally like a substitution step. So the idea is that we can type check without having to do any evaluation whatsoever, so I think that this is a way to get around it. And it's like, I think that this is an okay approach. I think that, like, it's not technically speaking what the textbook did, but, you know, no plan survives first contact with reality, am I right? So, anyway. Can I hand in a Go implementation of the project after doing it in Haskell? If you want, but there'll be no extra marks for it. We'll be marking the Haskell version, I'm afraid. But yeah. Anyway, might as well get to the lecture material then. I'm assuming that doesn't count as wasting your time because I was talking about the project, so that is probably going to be interesting to people, hopefully. So, we were talking about data structures. We were talking about how to implement data structures inside of our existing semantics. So, we're going to start off with the most basic data structure, which is the pair. Pairs, it's just it's a collection of two items. You access the individual items in the pair using projection. So in this case, dot 1 gets you the first one, and dot 2 gets you the second. I blow your mind with how pretty the code is. That you feel bad by not giving me bonus mark. It's up to the TAs, my friend. So we were talking about, like, if you were to provide a derived form for this, what would it look like? And of course, we already talked about how to do pairs way the heck back in topic 5, if anybody remembers that. So that's how you would do it. So let's talk about typing pairs. So, I'm gonna sneeze. Pardon me. Hey, Mark, you could do a implementation of Go in Go. Ha! He's like, already done, my friend. Already done. Full screen. So, yes, thank you. So, we've talked about how we would implement the semantic, and hopefully the semantic makes a reasonable amount of sense to you, because it's very, like, straightforward, right? So let's talk about typing. There are basically two ways we could go with this, right? The first, like, approach you could take is to say, you know, oh, well, implement Go in Haskell, then implement Haskell in Go, then create an infinite cycle. Yeah. Oof. So there are basically two approaches to typing that you can take. The first is to be restrictive about the types of the things that can go in the pair. You might be able to say, like, this pair is typed bool if every element in it is a boolean, right? This would make a certain degree of sense. We might even be tempted to say that the type of the pair itself is the type of either component, right? This sort of coercion, however, would make our pairs something very different from the derived forms discussed above. So in the derived form, that's not required. And it's also, like, fairly restrictive. It's not necessarily what you want. So, in case you haven't noticed the heading of the, unless you haven't noticed the heading of the next section, tuples are what we're going to be talking about next. And if you think about how tuples work in Haskell, they are heterogeneous when it comes to typing. right? So you're allowed to have like a pair in Haskell that's like bool int or like float some custom defined type, whatever, you know. Pairs. You can mix the types up in them, right? So a better way to think of this, right, is to think of it in the reverse direction, right? So we've defined a new value, right? The value is a pair of two values. What sort of type would this be a new canonical form of, right? It's like, let's think of it from that way. We've added a value, right? If you think about the other sorts of values that we've added over the course of this course, you know, when we added true, we sort of implicitly knew that true was always a Boolean. When we added 0, we implicitly knew that it was an integer, that sort of thing. So what is a pair? Well, this is what will be known as the product type, or Cartesian product. So the idea is we need a type that represents two types that are sort of, you know, slightly interchangeable. Right? It's like we want to recognize the distinction, for example, between a pair containing a natural and a Boolean, and a pair containing a Boolean and a natural, right? The ordering matters. So, product. So the question becomes, how do you represent the type of something that contains two types? Answer, we must expand the type system. So we will add the new type T cross T, or T product T. I'm probably going to say T cross T. This is known as the product, or the Cartesian product, type constructor. If we consider the total number of possible combinations of the two types there are, that is the cardinality of T squared. So that's why we use a product operator. It's like the number of possible, the number of possible product types is equal to the number of types squared. So that's, you know, where multiplication sort of glances in. It's like kind of flies in and then flies off into the distance again. Since we are adding this new type constructor, pairs cannot be a derived form, despite having a clear and easy implementation in pure lambda calculus. So we're sort of in the same category as, I can't think of an example right now, but, you know, let bindings, I think it was, that we needed, like, the type checker in there. But, the derived form that we're talking about here, in order for it to be an exact derived form, like, we've got the semantic side of it all kitted out, and that's fine, but we can't perform the same transformation and have the typing come through. So, because, of course, in this case, you know, you would be talking about, like, a arrow type, the arrow type constructor. Whereas here, this is a different sort of thing. You also have the advantage here with the product or the cross type constructor. This denotes this as being a pair. And it's useful to know that something is a pair, right? But yeah. So, the following typing rules intuitively follow our evaluation semantics. So, if we have a pair, the type is simply the type of the first one cross the type of the second one. Very simple, very intuitive. Projection, super easy. You project the first element of T, and you get the first type. You project the second element, you get the second type. Very, very simple. Aside from the use of the new product type constructor, these types are wholly unremarkable. In fact, one might even say they're so boring that certain people in the chat might be talking about gaming laptops instead of paying attention to the lecture, huh? Hem. One thing to note is that we are maintaining our pattern of having one typing rule per term of the calculus. That's, you know, again, a very useful and important rule. So, I'm going to assume that there are no questions about that and move straight on to tuples, yeah? So, some of the puns here are pretty terrible, I'm going to say, just off the bat. So, tip-top tuples. Just very briefly on the subject of gaming laptops, as long as you treat them nicely, they can last a very long time. I had a gaming laptop that lasted me 6 years. That was actually the one I had before I replaced it with this one, which is the it's the Republic of Gaming Toughbook 1500, I think, the 15-inch Toughbook, or Tough Gaming laptop. I still have the stickers. They've fallen down. See? I bought the official laptop, so I got the official sticker pack. There we go. Of course, you know, for me, I find it more useful since there's, you know, I have to work at the school and at home to have the laptop move between two places, but, you know. So, tuples then. So we've talked about pairs. Now let's generalize this. That's going to be like the next couple of sections. We're going to take we've taken the rule that we've established, and then we're going to generalize it for more interesting forms of data structures. Because pairs are useful, but not terribly interesting. You know, like, you'll use them a lot. You'll use them even for Project 3, but they're not terribly interesting. So what about tuples? Tuples are a straightforward generalization of pairs to data structures containing an arbitrary number of elements. Unfortunately, this means that we need to come up with a notation for uniformly describing systems of arbitrary arity. That is, we need a notation for lists of numbers. So, the textbook... So basically, the problem that you have with notation, mathematical and scientific notation, like, the constant problem is there's always a balancing act between rigor and ease of reading, right? So, in this particular case, for this course, I've adopted to a slightly more readable format that is slightly less rigorous. So, because it has, like, it doesn't declare the intermediate variable I. The textbook uses the following notation. It says, you know, t at I for I an element of 1 to n, right? But for me, because this is an undergraduate course, and, you know, it just makes it easier if we can read it easier, I'm just going to say t from 1 to n. T subscript 1 to n, and that'll be sufficient for our purposes. But yeah. Syntax! We will add the term on the previous slide to our calculus. So, a tuple in our syntax, still enclosed by curly braces. We have this t from 1 to n, and we also have t dot 1 to n for projection of any of the elements of an n tuple. Further, we will define tuples containing only values to be values themselves, fairly straightforwardly. And finally, we will also add the following type constructor. So we now have curly brace types. So the type curly brace, so this is like a tuple type, but essentially what this allows us to avoid is the messy, T1 cross T2 cross T3, etc., all the way up to Tn. Like, that is the same as this. This is the same, cross type constructor. Yeah. Good. So, evaluation rules. You may notice that the evaluation rules here are extremely similar to the evaluation rules for pairs. We generalize. So essentially, like if you pick a particular j, if you pick j as being 1 or 2, then this is exactly the same as the evaluation rule for pairs, right? It's a generalization of it. Furthermore, we have a congruence rule over any projection, and we have e-tuple, which is a congruence rule over the tuple itself. Now, this is an interesting one. There are some subtleties here. So, notice we've got v from 1 to j minus 1. Then we've got t at j. Then we've got t at j plus 1 to n. And that gets converted to, the same beginning at the same end. And tj. Is that the emergency alert?
Yeah, I just find it.
On the phone?
Yep. It's a test for the emergency alert system.
It's a test of the emergency alert system. Good lord. So this isn't like a Hawaii situation where it told them that there was a nuclear attack inbound and then it didn't happen?
Nope.
Okay.
Test message issued, yeah.
It would be during my lecture.
It would be during your lecture.
Jeez. Oh, somebody actually has a question about the lecture. So our tuple will not be the one from lambda calculus, right? They are something new now. Yeah, so pairs have an easy implementation in lambda calculus, right? You can just, the way that we defined it previously. In order to do an n tuple, you would essentially need like n abstracted variables. Like, it gets very, very complicated very quickly. So the preferred way of handling tuples is to make them their own term rather than putting them as a derived form. And it would be kind of like ridiculous to make them a derived form anyway, because like insofar as like T1 cross T2 is like not exactly lining up with our old calculus, you can imagine how bad this would be, right? But yeah. Yeah, so if anybody didn't get that emergency alert, check to see if your phone still has batteries. It's interesting. Interesting that they would do that like 5 minutes before the hour. Normally when they test stuff like that, isn't it like exactly on the hour that they test it? You can filter the alerts you get. I turned off some of the unimportant ones. It's a healthier lifestyle. No friggin' kidding. No kidding, man. Does the 1 to n notation allow unary types? That's a good question. Yes. It also allows 0. So we are allowing empty tuples as well. So yeah. All the hail the unary tuple. Yes. Why should the government be able to annoy me at will? Well, if there ever was like a nuclear strike against the city that you live in, you'd probably want to hear about it, right? Yeah. And, like, you know, it might be annoying to get the Amber Alerts, but it's also, like, a child has gone missing, you know? But, anyway. So, yeah, like, technically speaking, you know, if you're working with a unary tuple, then, you know, you have an empty tuple before and an empty tuple behind. And we're not really gonna, like, worry about getting into those types of nitty-gritty details. We're going to assume that you guys are intelligent enough to figure out that if the tuple is empty, it's a value, and then you don't have to, you know, there's no congruence rule for it, right? Yeah. So, God almighty. Now, so the projection, elimination, and congruence rules are straightforward adaptations of E pair beta 1 and 2 and E projection 1 and 2. The congruence rule E tuple actually describes a set of inference rules, however. Technically speaking, this is a set of inference rules, but that's okay. True to form, we control the execution of the elements of the tuple by requiring all elements preceding any particular value to be evaluated to values before the congruence rule can be applied. That is, to evaluate any element of a tuple, all elements to the left must be evaluated first. So that's how we, like we should be familiar with this form by now. You evaluate things left to right, evaluate it to a value, then you move on to the next one. If you don't have that rule, then the calculus isn't determinate, and having a determinate calculus is very, very important. So that's why we do things that way. So let's talk typing. Again, pardon me. My brain went short-circuited for a moment. Also, grammar not good. Again, the above inference rules should be relatively straightforward. So, if we have, like, if for each element ti of the tuple, it types to capital Ti, then the type of that tuple is a tuple of, essentially, of all those types, right? You can think of it as a tuple type. But it's really like T1 cross T2 cross T3, etc., etc. Furthermore, my God, that's a lot of text messages. Furthermore, if we have a projection, Tj, right? Whatever j is, you pick that out of the typed. You pick that out of the typing tuple and make that your type. Very straightforward. T-tuple states that in order for a tuple to be well-typed, each of its elements must be well-typed. And T-projection states the inverse. If a tuple is well-typed, an element projected from it will also be well-typed. So there you go. Cool. Any questions? Any more questions about tuples before we move on to records? Geez, we're moving through this material faster than I anticipated. Can we have an example for the type of a tuple with several values? Yes! Absolutely, we can have an example. So, let's do basic stuff. So let's say we had true, false, successor of 0, 0, and unit. unit with a lowercase u, which means that it's the value. So there's a tuple. It's a 5 tuple. It contains 5 things. Right? Just making sure that we are conforming to syntax. Yep. It's comma delimited. I know it doesn't say that like in the syntax here, but it's comma delimited. Can a tuple be a member of a tuple to create a tupleception and irritate everyone? Oh yeah, let's do that. Let's make the 4th tuple a tuple that contains 0, yeah. One and x assign 4 colon or semicolon dereference x plus 4. So, well, actually that doesn't work because it's not a value, but it doesn't have to be a value to type it. So we could have a tuple like this, like, because the tuple contains arbitrary terms of the calculus, then it can contain anything that is in the calculus. That is right, folks. A tuple can contain functions. A tuple can contain sequencing operations. A tuple can contain referencing operations. It can contain let bindings. And this is true of pairs as well. Actually, this is true of anything. So, they don't have to be values. They can be arbitrary terms. Most of these are values, but not all of them. So the type, then, would be bool, nat, a tuple type containing nat, that eventually would be, it depends on the location, but let's assume it's going to evaluate to a nat, and then unit. And there you go, that's your tuple type. Technically speaking, it would be like bool, cross nat, cross a nat, cross bool, or cross unit. Technically speaking, this is also correct, but, you know, it's useful to keep the brackets consistent. Like, this is what Haskell is actually doing, even though it uses the same types of braces for, like, the construction of the thing and the construction of the related data type. Like, a list and a list data type are distinct and separate entities, but they both use square braces in Haskell, right? It's to hook them up. Yeah. Good lord. That's a lot of text messages, but I'm teaching a class right now. So there you go. Tuples. So, now we've talked about tuples, let's talk about records. So, we got to tuples from pairs by generalizing over size. We can get to records from tuples by generalizing their means of access. So, the thing about a tuple is that fundamentally you're still indexing it numerically, right? So if we reorganize tuples so that they're being indexed or accessed or projected with something other than numbers, then we have achieved the generalization performed over tuples to generate records. So, whereas a tuple uses natural numbers as a means of accessing its members, we can generalize this to some element f of a set of field names f, with the cursive f. So, the textbook actually uses L and cursive L for a set of label names, but I'm going to use f because, number one, field names and labels are essentially synonymous. They mean precisely the same thing in this context, regardless of what they mean in other languages. And also, I want to avoid confusion with memory locations. Like, we're already calling memory locations L, so let's choose a different metavariable. Let's choose one that's a synonym that isn't L, so we don't confuse it. So F, field names F. The step from tuples to records in R calculus is roughly the same as the step from tuples to dictionaries in Python. Is that thing just going to keep buzzing periodically until it gets its thing cleared? Give me a second. I got it. Yeah, that's exactly what it is. It was just doing, like, periodic... It was just buzzing the phone periodically until I cleared the alert. No, that's okay. How were you to know the phone would be that stupid? Good lord. So, anyway. So, fields. The syntax for fields, the syntax for records is highly similar to that of tuples. This is kind of to emphasize the fact that these are basically the same structure at different levels of generalization. One might say a pair is a tuple that only contains two elements, and a tuple is a record that has sequential numbers as its set of fields, right? So, the way that you write this, you get your field names, 1 through n, you have an equal sign, and then your terms, 1 through n. To access, so to project an element of the record, you just do t.f, simple, simple. Similarly to its cousins, a record contains only values a record containing only values is itself a value. Thank you. So, sort of regardless of what the fields are, if everything in the record is a value, the record itself is also a value. And field names will also be necessary to look up the element type in a record type, so we should include the field name in the type as well. So, one difference, right? You have to include the field name as well. This is, again, whereas with a tuple we did this numerically, with a record we now do it with the field. So the fields have to be included in the typing information as well. Good. So, all three of our data structures so far have used curly braces to emphasize that they are very straightforward extensions of each other. The following evaluation rules are straightforward adaptations of those for tuples. So, to project an element out of a record, it's, whatever, if you have a record which has f1 through n is equal to value 1 through n, f at j projects value j. Very good. We have a congruence rule over projection, and we have this long thing, which is essentially the same rule as, this is essentially the congruence rule set up for records as opposed to, yeah. Yeah, it's the same rule as for records, where you have to have everything to the left evaluated to a value before you can continue. So, one of your esteemed colleagues in the chat has pointed out that we're kind of cheating here. We said we were getting away from positional arguments, but we're still kind of using them to perform the projection, right? So what gives? This is actually an interesting... So this is actually a... This is like a programming language design choice, actually. Some programming languages, despite what they tell you, will always be mapping the field names to numerical indexes. Like, for example, when you're doing structs in C, you are in fact working with numerical indexes which have just been mapped to labels, or fields in this case. it's sort of the difference between in Python, it's the difference between a dictionary and an ordered dictionary. But yeah, we actually have a slide on this coming up, but yeah. So, the evaluation rule, project record, relies on a slightly informal convention which we should make explicit. Yes. Oh, shoot. Oh, my God. I'm sorry, yeah. I should know better. I should have caught that during proofreading. What do we got? Record. What do we got here? Where is it? There we go, I think. So. Bop. Right. So. We're talking about this guy. This whole fishing out of the element with the field. So, if this is a record, and fj is the label of its jth field, then lost the curly braces now, too. I'm just not having a great day today, guys. Yeah, thank you. Actually, that goes here. Alright. There we go. So, like, the semantic that's implicit in this is that fj evaluates in one step to the jth value vj. Both this rule and project tuple could be reformulated to make this behavior more explicit. However, this would come at great cost to readability, so we will just keep the rule in the form listed. So you'll notice that, like, in this topic, we are finally starting to get to some stuff that has some, like, you know, we're starting finally to introduce things with real-world applicability, and we're finally starting to introduce more complicated things, right? As things are becoming more complicated, I'm having to hand-wave more and more of this, right? It's like, well, the explicit semantic would take up, like, a whole page, so, and you all know what I mean, so we'll just go with what I mean. You know, if you have any questions, ask me. But, you know, and that's kind of how things get towards the end of this course. It's like, this is why, like, it's reasons like this that we started the course off talking about, you know, explicitly, like, untyped arithmetic expressions. Because it's so gosh darned simple, you can go through the explicit semantic in its full detail, right? You know, as things become more complicated, it becomes less and less possible to go through the explicit, like, go through every nook and cranny of the explicit semantic, because it's like, you know, it becomes more and more of a research project or something that a PhD student would do if they were designing a new language from scratch to be able to go through all of this stuff. We can get the impression of how how it works. We can fill in, we can spackle over a couple of the gaps using our programming knowledge. But yeah. So, let's see here. How are we doing for time? We can do one or two more slides. Yeah. In some sense, the definition provided above fails to fully abstract tuple-styled numeric element access into record-style field access, as one of your esteemed colleagues has noted. Consider the congruence rule e-record. Following the Python example of dictionaries, it would be reasonable to expect something like e-record to be impossible. For example, like, note that we are, like, in order to evaluate left to right, we need a concept of left and right, which doesn't exist in the absence of numerical analysis, right? Or a numeric superstructure. Wait, what could a label be? Is it just any term or a value or something different? So, we abstract it to say they are the elements of some uninterpreted set. That set could be the natural numbers. That set could be the Booleans. That set could be strings. It could be characters. It could be floating point numbers. Anything that you want to put in the set is valid. But, if you really wanted to, you could do terms, I suppose, but, like, term semantics are already so complicated. You don't want to be evaluating your bloody field names, right? So you should stick to values. But yeah, the elements of some set. That's what the field names are. Often in computing, like real languages, they'll use identifiers. But we haven't really talked about identifiers, because this isn't a course in parsing. This is a course in language construction. So, following the Python example of dictionaries, it would be reasonable to expect something like e-record to be impossible. Like, if you think about it, dictionaries have no ordering, right? The order in which the for loop pulls elements out of dictionary is not to be assumed beforehand. The numerical sequencing of field names is relied upon to guarantee the determinacy of the evaluation of a record. If the set of field names was simply a pure set, no such ordering would be implied, right? So, take, for example, strings, right? Like, I suppose you could say, oh, lexicographic ordering over strings. Okay, sure. Take Booleans. What's first, true or false, right? There's not necessarily an ordering implied, which means that you can't construct it this way. The way we've defined them are closer to Python's ordered dictionary than to its default dictionary. And I assume the labels in a record must be unique. Not sure if this is said in the specification. Yes, they should be unique. Yeah. Yeah, I'm not sure that is said in the specification either. Let's see. No, I don't think it's said. But yeah, field names should be unique. There, I said it. Whether the language assumes unordered records are primitive or uses primitive ordered records and evaluation rules which allow reordering is a design decision that may have performance implications. So, in general, I would say that it's easier to have, like, performance should, in theory, be better with an ordered dictionary as opposed to a regular one. Because it should, in theory, be easier to find things if they're indexed, you know? But, who knows? Maybe Python has a really efficient implementation of dictionaries that supersedes ordered dictionaries in terms of runtime ability. Anyway, it's now 1:22 in the afternoon, so we are finished with class. If there are any questions, please ask them now. Otherwise, we will get the heck out of here. I'll finish Project 2, by which I mean Project 3. I'll finish Project 3, get that out to you guys hopefully today, and you guys can weep. Weep, my friends. My name is Ozymandias, King of Kings. Look on my projects, ye mighty, and despair. I'm actually, like, only facetiously building up the difficulty of Project 3. Project 3 is definitely more difficult than than Project 2, I'd say, but just because it's longer. Like, a lot of it is stuff that you've already done, and the main tricky bit is knowing how to manage mu and gamma. So many assignments, so little time. Yeah, I know. I already, like, axed one project on the midterm, though, so... You know, I can't not do this one. I won't allow it. Go have some fun before the nuclear missile hits. Yeah, seriously, though, right? That's an interesting moral question. If the world were going to end tomorrow, how would you act today? I would probably spend the day with my family. The answer is I can finally catch up on sleep. Yeah. Yeah, if you knew that there was going to be like a nuclear missile tomorrow, then probably the best thing to do today is to dig a little a bomb shelter, really. You know? That was a thing people used to do in the 50s. You'd just have a bomb shelter, you know? Somewhere on your property you'd have a hole that you could go hide in if the world exploded. It's not in fashion anymore to have a bomb shelter. Who wants to live in a wasteland? The pandemic was maddening enough. Well... Let's put it this way, right? Most of the thing that makes your life miserable is other human beings. So if you were like one of the very few human beings left, most of your problems would be over. You know? All you'd have to worry about is securing food, water, and shelter. Although, I suppose the few humans that were left would become increasingly problematic. I was thinking more like, you know, roving bands of post-apocalypse punk car drivers like in Mad Max. Anyway, take her easy, folks.